So what we're looking at, or what we have looked at in the past, is the addition with acids. So the acids one is a little bit more straightforward because you're dealing with H+, and that stands out as kind of a characteristic reaction or reagent, because we're used to seeing acids and bases in the past. This next section of our additions moves into chapter 12 in our textbook, which is an addition with electrophiles. And this becomes significantly more difficult because it doesn't fit any of our standard boxes that we're used to having seen. So try as much as you can to group and categorize these things or these reagents to help you find patterns to work through it. That said, those groups and categorizations have to come from an understanding of electronic structure. And that's where that reactivity of things that we've talked about in the past, electrophiles, nucleophiles, electron donors, electron acceptors, finding balances of electron density becomes so critically important. So again, we'll real quickly take a look at our acids, and then we'll look at the general idea for our electrophiles, and then we'll push into some patterns that I've seen within the reagents, and then we'll look at two more videos that kind of split out that reactivity. So with our acids, hopefully the thing that stood out to us is that we are starting with an acid, which means the most reactive thing is that H+. The pi bond comes out, reacts with that H+ to produce an intermediate. That intermediate usually set it up, or not usually, did set it up so that we had the positive charge at the secondary position. Our hydrogen goes to the position that already had more hydrogens, a la Markovnikov, but ultimately really what we're saying is that the intermediate forms the most stable carbocation. Now your nucleophile could come in and attack, and we get the product that we get. So cool. Chapter 12 is very much the same thing with our electrophiles, but the problem is because our electrophiles and our nucleophiles are so distinctly different from what we've seen before with acids are clearly H+, that we lose sight of that reactivity and we end up saying it's a whole new system. It's not a whole new system. You're going to start with some electrophile nucleophile system that may be connected, they may not be. The same process happens. The pi bond reacts with the electrophile, producing an intermediate where we would have the most stable carbocation at the secondary position, at least in this case. There's our electrophile, and our nucleophile comes in a potential step 2, and we would have our product. The exact details of what happens in that depends very much or very heavily on your electrophile and your nucleophile. Okay, so what you're looking for is these patterns to try and help organize your thought process. So for me, what I've noticed with these electrophiles is that they nearly always involve some aspect of cyclic characteristics. It can be a cyclic intermediate, it can be a cyclic product. This also means that we get more selective products. Okay, so they're better than acids and bases in that case because of that ring structure. We're limited to the stereochemistry. You can't have a ring going trans unless it's a really long ring, and that then limits the amount of reagents that go through and do it. So I focus primarily on the cyclic intermediates, and I went through and categorized each of the reagents and said, well, what would the cyclic aspect be? Okay, so in chapter 12, we get bromine, MCPBA, diazomethane, and a mercury reagent, and those are all forming 3-membered rings. Okay, chapter 12. There is another reagent in chapter 12 that forms a 4-membered ring, okay, or 4-membered intermediate, and that's our boron reagent. Okay. When we move into chapter 24, which for those of you who are like, but that's not on our list, it is on our list. It's a small section of chapter 24. I think it makes up two sections, like chapter sections. We encounter osmium tetroxide, potassium permanganate, and ozone. Okay, and those are forming 5-membered ring transition states. All of these reagents are following the same pattern. They have an electrophilic site that reacts with the nucleophilic alkene, and then they have a secondary nucleophile that reacts with the other reactive site on our alkene. And as we hopefully remember from our acid-base stuff, you should realize that an alkene really comes out as a positive and a negative, that we're really just looking at those two sources of reactivity. This is why the H plus goes to that negative and our nucleophile goes to the positive. When we switch to the electrophile section, it's no longer H plus, but it's the electrophile. So as long as we recognize that reactivity or that kind of characteristic of our starting alkene, we've already limited the potential outcomes that can come out of this. Okay? And that's one of the big powers behind this. Okay? So let's take a look at what these things have in common. So remember, our overall reaction was the alkene reacting with, and I'm nuancing it here a little bit and calling it a Lewis acid. Remember, electrophiles can be Lewis acids, right? But our alkene is going to react with this somewhat positively charged structure. Typically, it's not formally positive because we need to stabilize it, and that's the Lg, our leaving group. Okay? Then we might have the nucleophile present in the solution at the same time. So when we go through and look at the characteristics for that La, if our Lewis acid piece that we see as our reactivity can also act as a nucleophile. Wait, how can it also act as a nucleophile? That doesn't really make any sense, right? A Lewis acid accepts electrons. A nucleophile must donate electrons. There couldn't possibly be a structure that could both accept electrons and donate electrons. Oh wait, an alkene accepts electrons and donates electrons. So there are circumstances that, yes, this rule is satisfied. So really what we're looking for is that Lewis acid needs to be electrophilic, right? Because there's a leaving group associated with it. So that leaving group has to be stable. It has to be wanting to leave. As it leaves, that leaves our positive charge on the Lewis acid. So great. That Lewis acid must also have at least a lone pair of electrons. If it does, then the Lewis acid can act as a nucleophile. And you're getting a three-membered transition or intermediate. In this case, as we're drawing the mechanism, we're forming a formal intermediate. Okay? That typically means that Lewis acid is positive, though again, it depends on the specific scenario. Okay? And this is now where our nucleophile could come in, break open the ring, and we get our product. You'll note that in this kind of characterization that we've got this question mark floating out here, okay? Really in both cases. And that's because to decide if the reaction progresses forwards, we really have to evaluate, sorry, I'm going to spin some stuff around here. We really have to evaluate our intermediate. And if that intermediate is stable, well, then there's no need to continue on. If it's unstable, then I need to continue on. Well, how do I know? Well, look for that positive charge. If that positive charge is there, it's probably not very stable, in which case it needs to, if the positive charge is there, it needs to react because it's not very stable. It's charged. If it's neutral, well, now it's probably stable. It's not going to continue. And sure enough, that pattern holds with a lot of our reagents. If we switch it up to the other category here, in this case, Lg is still there, but now instead of Lg being a good leaving group, Lg is tiny. So what do I mean by tiny? Tiny means it's unstable. And if it's a bad leaving group, it can't exist on its own. And if we look at that first mechanism up there, that leaving group is leaving, right? It's leaving the structure. It's off on its own. When we move to Lg being tiny, if it's tiny, it can't exist on its own. Because it can't exist on its own, it must immediately react back, thereby forcing the Lewis acid in the leaving group to be connected to the alkene in one step. Okay? Both of these mechanisms have different results that come out of them as far as the alignment of the Lewis acid, our electrophile, and our leaving group. Okay? So what we need to be thinking about when we run these reactions is actually putting atoms in and then deciding, right? What is the structure? What are structural considerations that are going to force stereochemistry? What about the mechanism? In the four-membered ring, they're coming in at the same time. In the three-membered ring, they're coming in at different times. how does that force stereochemistry, or potentially even a fun word, regiochemistry, where the individual groups are connected, not where they are in space, but the atoms they're connected to. So what we want to be thinking about is these patterns. Those patterns will help us move through, and we'll get a better understanding of what's happening within these reactions. With that, thanks for watching the short intro. We'll look at the details here in a second, or in the next video, as soon as I get my mouse moving.